BC Calculus, Lesson 8.5, Applications from Science and Statistics. So we get back to work now, literally. We've talked briefly about work before. Now we're actually talking about using it on a regular basis. It's an integral because we're looking for applications of integrals. And it's relatively straightforward to use if you have the force function. So the integral from 0 to 1/2 of cosine pi x dx equals sine of pi x over pi 0 to 1/2, which equals 1 over pi basically. Sine of pi over 2 is 1, sine of 0 is 0, so 1 over pi, which is 0.318. If we have newtons and we have meters, then that becomes joules. Now we can make life very challenging. A leaky bucket weighs 22 newtons. We put some water in it, and it's leaking. And then we have a rope that we're using to lift it up. And the rope has weight. It's a big rope, probably more like a chain, but you get the idea. What's the work we do just lifting the bucket? Well, that one's not that hard. The force for the bucket is constant. It's 22 newtons. So the integral from 0 to 20, 22 dx is 22x 0 to 20. Multiply that, we get 440. And I didn't talk about it before, but that's the same thing as a joule, 440 newton meters. Okay, what about the water? Well, bucket starts at 70 newtons of water, and it leaks. It's got a hole in it. And I love this because I would assume we're lifting the bucket up to use the water, but it's empty when it gets up to the top. So the weight at 20, and I really should call this an F, but I don't. It's weight, which is another type of force, is 0, and the weight at 0 is 70. And I've seen some interesting styles of how to do this. I like to do a little y equals mx plus b here, where we're changing y on top. 70 minus 0 over 0 minus 20 is negative 3.5. In other words, it's dropping 3.5 newtons of water every step it goes, and it starts at 70. But I've seen it done lots of different ways, so that's just my way of doing it. So the work done is from, again, 0 to 20, and I'm going to rewrite this backwards. 70 minus 3.5x dx, which is 70x minus, I'll write it that way. No, I won't. Minus 1.75x squared from 0 to 20. So we need a calculator to blast this one out, and we should get 1400 minus 700 equals 700 joules. So somebody needs to fix the bucket or tell the idiots up top when they're lifting the bucket, if it gets lighter and lighter, then they've probably got a problem. Lifting the rope is a similar problem. When you lift the rope originally at 0, it has a weight of, I need to go up and check it out. It's going to have to be 20 meters long, and it weighs 0.4 newtons per meter. So 20 meters times 0.4 newtons per meter equals 8 newtons. And then at the top, after 20, basically equals nothing. So you've got something similar to what you just did. You find your slope, and you say the work is the interval from 0 to 20, and blast it out. 8 minus, I've done the slope part separately here without writing it down, minus 2/5 x dx. And the way I check that to see if it works is to say, well, what's the weight gonna be after 20? So 2/5 times 20 is 8. 8 minus 8 is 0. So my little model works. Again, doing the calculus gets us to 80 joules to lift the rope. So to lift them all together, we get 440 joules plus 700 joules plus 80 joules altogether equals 1,220 joules. So if somebody's lifting by hand, they're working pretty hard, and if it's a machine, then you can start to realize how hard the machine's working, that sort of thing. So next application, force, fluid force and fluid pressure. So if you ever look at a dam, it's actually much bigger towards the bottom than it is at the top. You've got your water sitting in here. And that's because the pressure is much bigger at the bottom. When I say much bigger, I mean much bigger. The dam failures through time can tell you that. So we can look at this as the pressure equals W, which is the weight density. And this varies per liquid. It really depends on the liquid. The denser it is, the more pressure, of course, it pushes down with. And then H is the height of the liquid. Now, that's actually the easy part of the problem. The hard part of the problem is understanding the geometry of the vessel we're discussing. And it could be a square, circular, it could be a big tank, it could be anything. Excuse me, not feeling so hot today. So here's a classic, 1919, January 15th, a 90-foot diameter cylindrical metal tank filled with molasses. And molasses has a weight of 100, a W of 100 pounds per cubic foot. So that was some serious pressure. It's 30 feet high, and it blew up and just devastated a huge chunk of the north end of Boston. And then worse than that, it's sticky stuff. So everywhere it goes, people track it everywhere, into shops, into homes, in the subways, out into the suburbs. It's crazy. So how do we do this? Nope. P equals WH. The pressure is 100, and it's at the very bottom, pounds per cubic feet, times 100, pardon me, 30 feet, 3,000 pounds per feet squared. Just so you're aware, pressure is always given as force per area, in this case foot squared. The most common one in America is PSI, pounds per square inch. Drawn like that. We won't get into too much of that. We're trying to give you some ideas. I do remember doing a lot of this in calculus, so yeah, that's pretty much what's going on. So they want to know what the total force on the bottom of the tank, and that's on the base. And there's a lot of problems with reading questions that are not written particularly well. That's just saying, here's my tank. What's the force straight down? So then it's just, there's no calculus involved. It's just, oh geez, that's 90 feet high. My bad. Where did I get 30 from? Seems like a familiar number. 90 feet high, so it's 9,000. So it's a pressure of 9,000 pounds per feet squared. Oh, it's a 30-foot. Yeah. And times the area of the base, which is 90 feet high, 90-foot diameter, 30-foot wall of molasses. That's where I'm getting it from. That's, oh, that must have been interesting. 10 pi r squared, which is 45 feet squared. So the pressure on the very bottom of that tank, which, it's got to sit on something. Everybody assumes the ground is perfectly solid, but it might have been on, platform or something like that. You never know. It's 57 million pounds. We'll throw some decimals up here. Pardon me, some places up here. 57,300,000 pounds of force. So that gives you an idea of why this thing broke. Probably not the wisest decision to keep it in one big tank. What was the total force against the bottom foot wide? So again, I said we're going to have a little trouble with keeping it straight what they're asking. This is a foot high. What's the total force against that? So now we need some calculus, because as we go up, we reduce the pressure. So we need a pressure type of integral. We know that the pressure at the bottom is 9,000. So that's the pressure. But we need to multiply it by the area that we're looking at there. So the circumference of this thing is 2 times pi times 45 equals 90 pi. It's a 1 foot high segment. So it gives us 90 pi feet squared. The pressure at the bottom is 9,000, but it varies directly as it goes up. So we have to write it as, what is the integral from 89 feet to 90 feet of 9,000? Where am I getting 9,000 from? Oh, well, I got to do the whole pressure thing. It's 100 times how deep it is, times 90 pi dy. Think about that one for a second. It's at 89, it'd be 100 times 89, similar to what we did up here, 100 times 90. It's at 90, it's that. In between, it's a linear change. So, do a little calculus, we get you'll notice it's almost always a simple polynomial, just y squared over 2. And I'm just going to cut to the chase. The pressure on that wall is 2,530,000 pounds. Which, yeah, that's a lot. That's probably why it ruptured. So you really don't want to put something really big and heavy like that into a massive container. So a little tricky on that. And then we got probability. What's the probability that a clock in your attic is stopped between 2 and 5 p.m.? So you stop and you say, well, I can write this calculus-wise. I can say f of t for time is, there's a 1 out of 12 chance it's any time you want between 0 and 12. It's 1 o'clock, 2 o'clock, 3 o'clock, whatever. And That's that 1 out of 12 chance it's that hour, because it's 0 all otherwise, we'll just say. And so we do the whole integral thing. This is the key. We say, oh, from 2 to 5 of f of t dt. So we know that we have a 1 out of 4 chance. Now, that's a stupid calculus problem, because if you just looked at it and said 2 to 5 is 3, there's 3 hours window. Clock is always on a 12-hour cycle, so that would just give us 1/4. But I did it calculus just so you can see a way to do it. Do not worry about that. Here's the ones that you need to worry about. So you look at probability as terms of area, and the area is under what is called a normal curve, which explains a lot. It's very, very, very popular. It's the bell curve. If you take a test, this is your mean, which is called mu sometimes. And then we say, well, how good is this data? How tightly packed is it? And we have something called standard deviation. Which is written as a sigma, which I'm having a lot of trouble writing properly, so that way I'll have to do. And then we've got certain rules for how much is covered. But as you can see, this would be an area. So if I asked you for what's the area of one segment over in the positive, you could do this kind of nonsense and all that. The problem is, what is the actual function? And it's hideous. It's hideous. It's not a pretty function. So let's see if I've typed it up for you guys. Yeah, I did. I don't know why I asked for the probability of the clock again. So I'm going to move on from that. I think I was going to do it one way one time, and I did them both together. So there's your mean, there's your standard deviation, and we're talking normal curve. So here is your probability function. You look at that and go, oh my lord, yeah, and it's bad, but I actually programmed it in to my calculator, so I don't have to deal with it anymore. This is your mean. This is your standard deviation again. I am sure this is in your calculator somewhere. I actually went looking for it, but didn't spend a lot of time, so I couldn't find it. So this is 68% of your curve. I'll show these three with this. Mean over 1 sigma. So this is 1 sigma. 68% of the area is under the curve. 2 sigma. 95% of the area is in there. That's actually a very important number in statistics. 3 sigma and 9.7%. So telephone helpline takes an average of 2 minutes to answer calls and has a standard deviation of 0.5. So the key is to say that's my mean. This is my standard deviation. It's my sigma. So what is range of calls answered from 1.5 to 2.5? Well, that's 1 sigma out, so we're looking at 68%. 0.5 to 3.5 minutes, that's, let's see, 0.5 is 1.5 sigma, and 3.5 is 1.5 sigma, so that's 3 total. So that would be 99.7%. Right, 3 left and 3 right. So almost all the calls. If you didn't get answered, you probably got a problem. So this is from industry. They actually take a bunch of samples. In this case, we've got frozen spinach boxes. They're supposed to weigh 10 ounces, and due to the machine packing them, or the people packing them, or whatever, they actually weigh 10.3 ounces with a standard deviation of 0.2 ounces. Assume the weight is normally distributed, which you can almost always assume, because otherwise we can't do these problems. So we're looking at that formula I just gave on the previous page. What's the percentage that they can all have a weight between 10 and 11? So you do f of x equals 1 over 0.2 root 2 pi e to the negative x minus 10.3, there's my mean, squared over 0.08. And that is 2 times sigma squared. Yeah, so there's a lot there. It's easy to screw it up. Although, I just put it into my calculator and just ran with it. So we do the integral from 10 to 11 of that f of x, and we get 0.933. There's a 93.3% chance. Now, what percentage would we expect to weigh less than 10 ounces? So basically, we're going to the left forever. And if you think about the normal curve, I mean, it goes forever out here. So I've done something. I've looked it up a few places, and they're like, oh, yeah, don't worry about it. Just go out a couple sigma, 3 sigma, 4 sigma. I go out 5 sigma, and that's been working. So to do that, I literally say, all right, 10 ounces, 5 times sigma is 5 times 0.2 is 1. So then I change the problem to what's the probability that it's from 9 to 10 of f of x. It could be less than that. I could write 8 or 7 or 6 or 5. The answer won't change to the significant figures I'm looking for. 5 sigma works for me. I mean, play with it and you'll see it's really a very, very small change. And we get a 6.7%. Try it in your calculator, try 7 to 10, and you will get the exact same answer, because it's really not there in terms of you're so far down the curve that it's a minimal. We're going to do this when we do improper integrals. That's coming up soon. So what's the probability it weighs exactly 10? Well, if we did an integral from 10 to 10, you should know. I'm just going to get 0. And that makes sense. It's going to be incredibly rare that there's going to be, a million spinach boxes. There's going to be one that's exactly 10. It's going to be 10.001 or 9.999. It's going to be extremely rare. So when they say that single one, we just have to say there's an infinite number of things here. So the chances of actually hitting it right on is so small as to be considered 0. That's a boatload of math. Good luck, and as always, happy mathing.